For this talk was really, I worked now several years on IGC as a really practical tool, and I thought I give you a little bit of inspiration what can be done with some examples. And so I called it the beauty of new IGC applications. And I have certain examples to inspire you. One is BET surface measurement, specific surface management with water vapor. Of course, I've done during my PhD studies, I've used liquid nitrogen conditions, and I found by water, it's really something special. Another thing is I would like to go a little bit more into the flat surface investigation. And third, something which has not been mentioned today, but I found quite interesting because they use the same equipment here, is diffusion coefficient measurements, and to go into this. So first, my first example, specific surface area by water. So the question here was really, how does the sample interact with water vapor? That can be soils, as my example, or it can be cement samples. Results on cement will be published quite soon, but I cannot talk about this today. So the samples I'm talking now, and which I can talk more freely about, are hydrophilic and hydrophobic soils from Australia, from Western Australia. And the question was here, what is the difference between wettable and between repellent soils? The idea was really to use water. It can be injected also, and the desorption curve can be interpreted. Analysis with a thermal conductivity detector, which is relatively easy to change also. And the question is now, so what is about the specific surface area and maybe about the heterogeneity of these two different samples? Here are the desorption curves, and you see already that the blue and the red curve are quite close. That's the absorbed amount at different relative pressures. And interesting here is that these curves can be interpreted in terms of BET. So quite different from what you probably know about BET measurements. And really good, it gives an excellent BET regression also. So this relates then into specific surface areas of, in this case, 8.7 and 8.0 square meter per gram of the two different samples. And compared also with other samples, this measurement, this BET surface measurement relates quite well to BET under liquid nitrogen conditions. We went a little bit further. We used not only water vapor, which I found so quite exciting, but also hydrophobic small molecule dichloromethane. So how does this relate? We made the measurements again. You see here the graph of the relative pressure and the absorbed amount. This relates also into specific surface areas, and you see they are smaller, the detected areas are smaller than with water, which is kind of what you would expect, but the differences are relatively small. Surface heterogeneity, yeah, there come some small differences, but not really so convincing, I would say so. So we discussed also what other resources of difference could be between the repellent and the wettable sources. Actually, it contains 2% organic carbon, and it has mostly probably a lot of proteins. I cannot have an answer to this riddle, but I can tell you with the IGC, we would say, yes, it has different specific surface area, but it cannot really explain so much the repellency and wettability. I think there should be some other answers here possible. So it was a good tool to detect specific surface area with water vapor, and that's the story you should keep in mind. My second story relates to flat surface investigation. So we already talked about how to measure flat surfaces. They're coated metals, sheets, films, and polymers. And here my story goes in two different directions. First, we have seen this, the concept about the chromatographic path. You can apply standard IGC infinite dilution or finite concentration tests. Yes, that's possible. And you can get normal results. Let's talk about adhesive films. You can characterize on one hand the polymer, the sticky film, or you can characterize the substrate. And you can see how are some compatibilities and maybe some optimizations. There's a lot of open issues, but I just would like to share this here. You can draw the polar interactions and the apolar or disperse interactions, disperse surface energy. And you can see where are the adhesives, where are the substrate, and how do they stick together, and when do they stick together, and when there are problems here. I know, Stephen, you love adhesion, and there's so much to talk about. I would like to do many more tests on this to understand this better. I think that's great potential. And for all the ones in the audience, having this in mind too. I would like to go now to different example that's about coated or treated metal sheets. And here I can go more deeply because that's something we can talk about. First, we can characterize the BET surface area directly on the sample. And that was for, at least for some contact, we had a real highlight that we can do this in situ at a plate 10 by 10 centimeter. Let's go to the example. The issue was the following. They wanted to have a really clear purification of the sample. And there was a normal surfactant degreasing step or a different alternative treatment A. So which one of the treatment is better in the outcome to compare the cleanliness of both treatments? In this case, hexylamine and hexanol were probes for the cleanliness. So the more they stick to this, to the surface, the cleaner the surface was. And here you see the specific surface area for both hexanol and hexylamine. And you see for treatment A, you regain a much higher specific surface area than with treatment B. So that's really a very good indication that treatment A is better, and you can quantify this treatment here in a sense. Also, treatment A is more homogeneous in the sense that hexanol and hexylamine absorb with the same specific surface area. Here we have the absorption energy distribution function going into more detail also, and this comes kind of automatically if you interpret the desorption curve to see which kind of sites and how much are being treated by the purification way. So you can see also here are differences between the hexanol and the hexylamine. So especially for the hexanol, there are differences, but which has also shown as a sum with a specific surface area. Now, to an example I like also very much is the diffusion coefficient by IGC. There is a current determination process, and yet this uses the Van Deemter method. Here, the flow rate is being varied, and depending on the changes of the peak, the diffusion coefficient is being determined. So that's a little bit of an indirect method. With the technique which we are using, it's a more direct one. So what we're doing here is really we saturate the pores and the particle at a certain partial pressure. Then we stop the flow of the probe molecule and we have a desorption. So you can imagine the probe molecules which are inside the particle must diffuse out of the particle. And this is a measure by some calculations of the diffusion coefficient, so quite direct. That's called zero length column because what should be avoided is a reabsorption of the probe molecule on the outer surface of the different particles. So very, very small chamber here, but the principle is quite similar as with IGC finite concentration. So saturation and then desorption. So let's see what comes out of this. So first, a little bit of theory. Here you have the equation and some references, how it relates to. And important is if you have a logarithmic graphic of the concentration and C0, then you can draw this. What is also important is that you have a very good reproducibility of the experimental setup, and that's shown here. So the feeding of the probe in a small concentration is really possible also using the syringe equipment with the automatic sampler. And you see here actually 3 curves on top of each other, or actually you hardly see anything on top of each other. That's the way how reproducible it is. So this is a desorption curve in a logarithmic graphic, and you see it becomes linear after some time, even though the concentration becomes very, very small at the end. But this region here is very important because this is a kinetically controlled region. So where the last parts of the molecule diffuse out of the porous particles, and this contains the information of it. Going to the examples now, we examined 2 different alumina beads. Slightly different diameter, but the diameter is part of the equation, so that can be done too. And here you see different diffusion coefficients of toluene, cyclooctane, and N-octane in these alumina beads and the practical measurements of this. You see also that there are different diffusion coefficients, quite different for the N-octane, which is larger numbers than cyclooctane and toluene also. You see also small differences between the single alumina beads and the different characteristic of N-octane with the B12 sample than with the B17 sample. So that's the transfer of the saturation, not of the surface, but of the pores inside the catalyst, and the extraction of the information from the desorption curve. There are many more possibilities here if you think about this. First, you can really take advantage of the very flexible use of any vaporizable probe. It can be corrosive gases, as in some cases. It can be also functional groups. So if you're working maybe in the rubber industry, double bonds might be quite interesting. Or you can add more groups here. So take advantage on this one. Also, having the possibility to saturate the surface or the pores by a constant flow with any probe really gives you an opportunity to measure diffusion coefficients or reactants of your interest in the sample of your interest. So this might be very good for catalyst research. Also interesting, specific surface area measurements with any probe. So you can take water, you can take a more hydrophilic probe, and this maybe goes into the direction also what Stephen was mentioning. So be creative in what you would like to measure, and not only specific surface area measurements, but also the heterogeneity here. Take advantage of this one. That's something we already mentioned, the choice of probes for the HSP sphere and the measurements. Yes, if you take 20 or 22, it doesn't really matter so much if you have an equipment and automatic equipment, which you really can use the advantage of taking a lot of different polar and apolar probes. Also important here, detectors for organics and inorganics. So we have the FID detector, very sensitive, good, but also a thermal conductivity detector for gases like water or other gases. And finally, yes, we have seen in the poll that there are quite a few people interested in flat surfaces. Take advantage of this device. It's really a great tool too. With this, I would like to end really. So you have 15 or even more samples. How would you like to characterize the samples to take the advantage of what they have on properties to extract the knowledge of your unknown properties of your samples? Take your opportunities here and use your imagination for your experimental setup. We are happy to answer any kind of questions, yes, please don't hesitate to do so. With this, I would like to conclude and hand over to you.